Welcome, my digital pathology trailblazers. This is our last paper that we're going to be discussing, and it's called The Future of AI ML in Medicine.
Learn about the newest digital pathology trends in science and industry. Meet the most interesting people in the niche and gain insights relevant to your own projects. Here is where pathology meets computer science. You are listening to the Digital Pathology Podcast with your host, Dr. Alexandra Zhurov.
We're actually going to be discussing two aspects today. One, machine learning and AI operations, and the other one is the future. So all the stuff that we can imagine that can happen with AI, virtual reality included, and different things they discussed in this paper, and that's what we're gonna go through. And let's dive into our topic. Well, so machine learning operations, and I had here this little asterisk with word machine learning graveyard. So obviously this is something cool, machine learning, and I talk about image analysis right now. Everybody can now get a commercial tool and start developing image analysis models. And then what are you going to do with those models? How are you approaching? There is a place to play with it, but then if you actually want to use it, there is a method to this madness that is gonna help us prevent this machine learning graveyard. There are several different algorithms that I was involved in developing that never went anywhere. I put a lot of time annotating them and nothing happened to them, which is part of the of life, right? So not everything gets deployed. These machine learning platforms is something that is like a framework somewhere where it's a software, but it's somewhere where you can utilize it as a computational pipeline, and you can develop pretty sophisticated algorithms in there. And in those platforms, you can standardize and automate the stages of machine learning model lifecycle. I like this lifecycle term. So you can then develop your model, everything from development through validation, deployment, and performance monitoring, which are the components that have to happen if you want to have this operationalized. So from this operational perspective, machine learning platforms are these centralized ecosystems in which data scientists, engineers, and analysts, among other stakeholders, so developers, physicians, pathologists, radiologists, whoever is taking part in machine learning operations, can interact, collaborate, harness data-driven insights effectively. And these platforms typically integrate a suite of tools and services designed to streamline the entire machine learning lifecycle. So if you are serious about machine learning operations, then you will think of the machine learning lifecycle. And how does that work? And it works on a macro scale. So like if you have really like operation, but it also works on a micro scale if you are developing something in a commercially available software. So the DevOps, the operations, you are designing the model, then you develop the model, then you put the model into operation, and you see that this is not okay from here. Well, it is as well, but not only to here, but you go back from operations to developing, and you go back from operation to designing. Pretty often, it's a very iterative process. So when you design it, both on micro and macro scale, a certain criteria and requirements, prioritize ML applications, think of a commercial offering, harvest your data. Data is tough, and good data is even tougher than data, but we have it. Just the harnessing and harvesting is difficult to have something structured. Then when you develop a machine learning model, I love their images. They're so cute. He's developing an AI robot. you prepare and process data. So, you harvest it here, then you have to prepare it. If it's not prepared, it's not going to be useful. Then you develop your different features, train your model, experiment, which is an important part. Like there is place for experimentation. And then you analyze and reflect on your performance. And if it's good enough, and to check if it's good enough, there was a separate paper on performance metrics. So you can go back to that one. So putting machine learning model into operation. So once it's good enough, you do the initial deployment, and then you have continuous integration and continuous deployment workflows. So you have something that you have to integrate into everything that you have in your lab, that you developed previously. And I have seen some cool developments at USCAP, at ASCAP in Boston, the Conference of United States and Canadian Academy of Pathology. And I have seen companies collaborating. Specifically, I was doing a podcast with Techcyte. Techcyte has a comprehensive machine learning platform for diagnostic purposes, for pathologists, for clinical pathologists, for anatomic pathologists. So Techcyte has this platform where a pathologist goes in and does their job. But there is another platform, Aphoria, for image analysis development, where you can develop image analysis models. And now they have an integration. You can develop something in Aphoria and do this DevOps cycle, and then deploy it in Techcyte in a non-research environment for pathologists to use in that institution. And the institution was Mayo Clinic. I thought that was super cool that you can now use this tool for developing and then deployment as well. And they have all the integration. So once it's integrated, then you have to do surveillance and monitoring. So assess data drift and trigger how do you deploy automatically. How does it get used? Because if it doesn't deploy, doesn't like have triggers to get deployed, the users are not going to get access to whatever this model is doing, right? I'm not going to like stop my pathology workflow and go click search for something. It has to be shown to me. It has to be already deployed. And there are important components of these platforms, different frameworks, software frameworks. So we are very much here in the software development world, and in the computational science / software development work. And there are principles of software development, and they apply here as well. By the way, there is a cool podcast that I just published recently with Dr. Hamid Tizoush from Mayo Clinic, and he has a super cool perspective on AI. And he says, well, it's not quite ready, even though I'm here like speaking about it for the 7th week in a row. It wasn't in a row, but for the 7th week about AI potential in pathology. He says like everything that's out there requires some more work. So you can check that on YouTube or on the Digital Pathology podcast. And he talks about, why did I even mention him? Because he talks about how software fails, how software should fail, how software should fail in the medical space. And he goes a little bit deeper into the principles that should guide AI development for pathology and for medicine. A really cool, like a non-nonsense approach. Say it as it is, say it where it is in terms of advancement where we are. And I like this type of conversations that are not sugar-coated. So go ahead and check it out. And in the meantime, let's talk about these platforms. So we will use various tools, libraries, capabilities to support the entire life cycle. And these environments will support experimentation with different models, model architectures, and setting to optimize model performance and validation of models using variety of performance metrics that we have in, let's check which number, performance metrics we had. Statistics in medicine, number 4, Livestream number 4 was on performance metrics. And then there are also guidances that you can apply, but this is what you will need to know, and you will need to use when you're developing these platforms, or when you're using commercially available platforms. You will have less development, but you still will need to validate, assess the models and things like that. And it would be fantastic if things would be standard based. At some point in this development cycle, it has to be standard based. So, and what they say here in this paper is that, broadly speaking, machine learning operation standardization is any enterprise involves adopting best practices, model development frameworks, and tools that are shared and are well understood within the enterprise, facilitating collaboration, reproducibility, and scalability of workflows, and reducing errors. So it has to be state-of-art stuff if you actually want to deploy it in an institution. What do I mean by state-of-art? Like, you cannot have gaps in the methods, in the frameworks. Like, this is already a commercial product. Like, in the research space, often different research areas are siloed, and you develop a very, very detailed, very deep expertise in something, but the things surrounding your expertise, you don't have so much expertise in, and you might be using outdated methods, outdating whatever, right? That cannot be the case when you want to use a machine learning platform for medicine. And that's why this is a multidisciplinary and multi-expert endeavor. So the things that you're going to hear being mentioned, and if you're already in this space, then you know about this, but I'm a pathologist. So, for example, version control systems like Git, containerization like Docker, orchestration tools, and data and metadata mapping. We're going to talk a little bit more about this. Version control system is something that controls versions, right? You had a version 1 that did one thing, and then you improved something. It has to be version 2, next version, next version. And people who develop software know that. People who work in a regulated environment with software know that version control and also audit trails, so like trailing all the accesses, times of access to the software, are features that need to be included in these platforms. So the data and metadata mapping takes us to one of our favorite subjects, DICOM, Digital Imaging and Communications in Medicine. It's a standard that is like a data map for medical images, and whole slide images can be mapped like that as well. So what does that mean? That we're gonna need to map them with the laboratory information system as follows. Tissue, for example, if it's a prostate, it's gonna be prostate, specimen biopsy, stain H&E, file type, DICOM. So you have to map these metadata. This has to do with the triggering of those systems, because if a certain piece of information is available in the metadata, then a certain model can be triggered. And if it's missing, then it's not going to be triggered on the sample. Yeah. So for example, if we want to automatically analyze all the prostate biopsies with a certain algorithm, there is going to be a trigger. This doesn't have to be the trigger, these mapping, but it is a very easy one. Like, you can deploy, for example, an image analysis on all the samples and do tissue recognition. And when you recognize prostate, then that's your trigger. That could be a trigger, but it's a very computationally heavy trigger, because you have to perform the computation before you even you have to perform one computation before you get the trigger to another computation, which is image analysis of the sample. Here you have metadata, so it's like easier, less computationally expensive. And there is something for machine learning models that is also mapping. It's called model cards. And these are standard structured documents that can be used to communicate key information about a machine learning model. So let me show you a table of this. This is a table of a model card in pathology. So we have on the left of this table, this is table. So we have the component of a card, and then we have a description. And component is basically going to be a piece of information. So like model name, model description, pathology, laboratory domain, disease condition, biological specimen, testing methods, and so on. And we have here 1, 2, 3, 4, 6, 7, 8, 9, 10, probably 25 different components. So, for example, it's going to be the unique identifier assigned to the model. Description is going to be a brief summary of what this model is doing and functionality of it. Pathology, laboratory, domain, specific area, or laboratory medicine the model addresses, for example, histopathology, clinical chemistry, all these things. This is a machine learning model card. So it's like a map with different metadata about the model that can then map with other stuff and trigger deployment of a model. And what about our deployment strategy? Yes, you need a strategy for deployment. And that's probably even more difficult than developing this whole model. So deployment strategy is going to be operationalizing a machine model, and this is going to present a pivotal decision around certain deployment strategies. What are we going to be talking about? On-premise, cloud, and edge computing. On-premise deployment, we kind of know what that is. It's on-prem, unlike your server computer, and the advantage of this is the direct control over data security and compliance. This is when I hear discussions about it, this is the one that is like the main advantage. You have control of it. The regulators come, you can show where it is, you can put your firewalls, all that stuff, right? Whereas cloud deployment, the advantage is scalability and elasticity. You are scalable, it's in the cloud, so you can use more or less computational power on demand. You don't have to, you can make it a lot more flexible than your stuff on premise, right? What is edge computing? Edge computing is like computation on machines. And this has started to emerge as an efficient process to compute in tandem with clinical data generation. So let's take our whole slide image. The whole slide image is being generated on the scanner, and you compute stuff on the whole slide image. So for example, you can already detect the nuclei. If you need to count something, you can do quality control, and one company that does that is PromanA, and they don't call it quality control, they call it quality assurance, because if you do it while you're scanning, and do something before anybody sees the scan, you assure quality. When you do quality control, they say, then you've already generated something that was not good quality, so you add work. They call it quality assurance, and they say, okay, you can do it while generating your data. And the advantages is that it can minimize latency, enable localized processing of data. It can allow you maybe a little bit more flexibility for checking things, deploying different algorithms, because you're doing it in the same place where data is generated. So then you have a data package that can securely go further in your pipeline, and not having then generated some data and then using an algorithm that maybe not be secured. You do it before, and then you take care of the security while you're transferring your data with everything. I hope it makes sense to you. And the problem is that it's new. And why is it a problem that it's new? Well, it's not not everybody has it. Only few providers have it. Only few people know how to deal with it. But once we figure out how to deal with it, once we figure out how to integrate, how to leverage it, that's going to be something that's going to be it already is one of the deployment strategies, but it's more on the edgy side, edge computing. What did I want to say? So there is, before the 90s, Poland was a communist country and not that high resource country. Now it's a normal resource country. And I remember this show when somebody bought a new washing machine and it broke, and the technician came and was like, of course it broke. It's new. What are you expecting? There was always adjustments to new stuff. It's new, so it broke. I don't know if it probably is not as funny for you as it is for me, but maybe some people can relate. Anyway, it's new, so it breaks. You have to figure out how to troubleshoot it, how to integrate it, and then you can leverage the whole benefits that come with this tool, in this case, edge comp. And then we have to figure out how will we get, or well, we have to figure it out ahead of time. How will we measure the return on investment? Because it's a significant investment, mostly like organizational resources, time, effort, obviously the tools that you have to pay for, but it's basically like an operation to have that stuff deployed in an organization. And then you can reap the benefits, but you have to measure your ROI, return on investment, and you can measure it by assessing improvements in patient care, related outcomes, operational efficiency, cost savings, business outcomes derived from deploying machine learning models. A lot can be gained when we enable automation and scalability of machine applications. So we have to think, why are we doing it from the business perspective as well? As we said at the beginning, digital pathology, machine learning, AI in pathology, multidisciplinary, multi-expert endeavors, and the institutional economics expert are part of the endeavor, part of the decision-making team, part of the evaluation team. Was it successful or not? And obviously, I love what Brennan says, bleeding edge. Yeah, bleeding edge. Exactly. It bleeds. But then it stops bleeding and it works and is stronger, right? So that was about the operations. And the main message is put some thought into it and get the right experts on board. And otherwise, it's going to fail. And now let's talk about the future. And now we are going to talk about some science fiction. Now about reality, future reality. The future is now. So let's start multi-agent frameworks or multimodal. Yeah, let's talk about multi-agent frameworks. That's a relatively new concept. I learned about it last year. Actually, I listened to a presentation by Modella.ai, and they have models and they have agents. And agents are actually, an agent is a model, and then you have multiple of them passing information to each other. So in our publication here, they say that multi-agent frameworks represent a sophisticated approach in which multiple AI models interact directly with one another to achieve complex tasks and optimize decision-making process. And there are frameworks like AutoGen and CrewAI. They are designed to mimic collaborative behavior seen in human teams, and each agent contributes specialized knowledge and skills to shared objectives. And they differ very much from the fundamentally developed. These frameworks differ fundamentally from traditional or single model approaches by offering diverse perspective of identical input. And why is that? Like, why do we need to have so many if we decide to have them? Because, and there is this concept explained a little bit further, the general intelligence. Basically, we don't have anything with general intelligence. We have stuff that is narrow, weak AI. It's still very powerful, but for just a specific task. So artificial general intelligence is designed to theoretically, and I highlighted theoretically here, perform any intellectual task that most human beings are able to do. And we're not there yet. And I think I started like talking about it maybe 4 or 5 years ago. And there's this division of different artificial intelligence. One is narrow, which is all the algorithms that we have. Then there is general was one of them. And there was something else, like different stages. And the general is still not there. But what we have are agents, different agents. So we basically now can orchestrate that deployment. We can orchestrate the deployment of various narrow AIs and not have to manually pass data, pass outputs from one model to another, because then you have to also hire a full-time person to do that. We don't want to do that anymore. We want these AIs to communicate with each other, have dependencies, have graceful failing mechanisms in place. And these are these multi-agent frameworks. And it's important to distinguish them from multimodal models. So multi-agent frameworks are these different AIs talking to each other, whereas multimodal models, they integrate diverse data types like imaging, text, and genomic data. Historically, you had unimodal models because we didn't have the capabilities. You would do one model for text, one model for image, one model for something. Now you can have a model that deals with all different types of data. And then once you have that model, you can put it into an agent framework. You can make an agent out of it, and then it's going to communicate to other agents. So for example, there's going to be an agent that retrieves images for this model. The other one retrieves text. The other one, whatever the other genomic data. Then they bring it to this one multimodal. Multimodal does something, and then another one writes a report. So let me show you an image on that, how this is envisioned here and how this could happen. So we have the inputs layer. So we have medical history. So here we have different data. We have radiology imaging, patient samples, information about the patient, like lifestyle habits, right? And this is all the data. And then we have agents layer. And we have these agents can work with the data and like retrieve data, but they can also help the medical professionals actually doing the work and generating the data by helping schedule appointments, helping them actually get the report on time, like sending automated emails that something is ready so that they don't have to go and check and have some kind of notifications, even maybe deploy some machines. But basically, they can help coordinate the work of the team. And our output from these agents is going to be what we usually put out, which is going to be the diagnosis or treatment plan, final report. But we basically augmented our whole work with AI agents. Let me just call them agents. That's what they're called. So that's one thing. And we already talked about general intelligence, that it's still a theory. And despite the promising potential of future with artificial general intelligence integrated, it is currently not part of our AI arsenal of tools to employ. Most of our current AI applications, they are narrow AI. And that's okay, guys. Like, it's fine. We can orchestrate our narrow AIs. We can still control them, have the human in the loop, and basically make sure that we're providing the best care we can. And agents are actually not that like futuristic. They're already happening. There are companies doing this. On the side of consumer AI, I have been looking for some agents to streamline the educational content creation. It's not where I would like it to be. So there is no like out of the box tool that I have seen that is you can click the button and it's gonna make you a podcast out of a YouTube video and things like that, as there is still a lot of manual work involved or very targeted specific development work. But that has been the case with all the technologies that now have softwares that are stuff that you can click, including image analysis software. So I'm kind of waiting for this to be available. And let's see when it happens. And when it happens, I will probably test it out and let you know what I thought. So, but virtual reality and augmented reality, this is also not new, but it seems a little bit more futuristic to me. I'm not doing the virtual reality world exploration. I think Facebook and like different platforms, people who do gaming, if you do gaming, let me know in the chat, then I can talk to you how it works. But basically, it looks a little bit like from Mission Impossible, which already is a movie from, I don't know, probably 10 or 20 years ago. But you have these sets, the visual sets, and then you have some sensors on your on like your head, on your hands that orient you in space virtually. And this is perfect for training, for learner engagement, and you can basically provide an immersive learning experience to without having to do this stuff to learn. So, for example, surgeries, you can do like that. You can do virtual surgeries. You can, like, for example, have people train virtually on blood collection or anything that requires patient, and only let them do this on the patient when they have passed a certain skill level on this virtual training system, and you can set it up that it actually like monitors all the movements or the things that you would need to do if you were doing it on a person, but you don't have to practice on a person. So that's definitely a lot better for the patient. You basically let the patient be assisted by a trained professional. You don't have to let or like the inexperienced training on people is minimized, which is fantastic. And for example, in pathology, something that could be done virtually would be a virtual fine needle aspiration. Clinics can simulate patients' experience, needle localization procedures, and even smearing on glass slides using virtual handheld device tracking. So this all could be done virtually. Is super cool. And at conferences, you will see, especially image analysis, software. This is all software companies, they might have headsets. I envision that in the future in the glasses, the smart glasses, I don't have mine on, but these meta glasses with the camera, the next version will have a little display. So it's going to be possible. And then you like move your screen in front of yourself without actually having a screen. Super cool. Also something that can accelerate drug discovery, identifying potential drug targets, and repurposing existing drugs for new therapeutic uses. I think I saw this already. That's not virtual reality. That's just, AI for the future. I saw this for predicting how proteins will fold. I saw this for designing antibodies and for different biotech procedures involved in drug development. We can also have something called virtual assistants, and it's an AI assistant. Virtual assistant can be, I know this term as somebody who's like not in your, no, I don't know, not like in your place. Like you can have virtual assistants from abroad that help you. But now you can also have an AI virtual assistant, and this could simulate patient interviews in medical training, offering real-time feedback and responses based on user inputs. And now with LLMs, you can totally have it. You can like conduct an interview and you have a program that is supposed to have a certain condition and already knows what this condition entails, and also like is pre-programmed how they should behave. Maybe like you need to ask specific questions. The assistant is trained not to reveal information before you actually ask, so that you can hone on your patient interview skills. And obviously something that is omnipresent in all the apps is gamification, and by analyzing learner performance data and dynamically tailoring change content to feedback. This has been out there in learning apps for a long time. So the app I'm using that definitely uses it, Duolingo for language learning, where you like have all kinds of games. Like you can invite a friend and then nudge them to actually learn. It's fun. And then it learns what you do well, what you do not do well, and it adjusts the learning to however your progress is, right? And it employs something called spatial repetition. So it brings up the stuff that you know well at the with a less frequent cadence, and the ones that you still need to work on with a higher frequency cadence. So perfect for like tests and things like that. There are different apps that employ that already. Quizlet, like I love it. It's backed by science, how we get engaged, how we want to progress. And I'm a little bit fascinated by how people learn, how adults learn specifically when you have a whole life to handle in addition to whatever you want to learn, and especially if it's something that is not crucial for you. If you must learn something, you will, if like your salary depends on it. But if it's like I don't have to learn Chinese, I don't know if I will ever speak it, but I decided to give it a try on Duolingo, and I am on my 102 days streak. So yeah, I can say a couple of words. I'm not gonna be showing off here because I'm still a little embarrassed. But that's that for education, for drug development. Oh, something I love and I wanna leverage more to basically publish more, because my main avenue of communicating these things is online. YouTube, super low hanging fruit, but also super low hanging fruit in terms of the input from other people, in terms of like peer review, in terms of like polishing you and publishing it in the scientific world, right? So now you can very much leverage AI for scholarly research. Large language models have emerged as valuable tool for literature search, summarization, and synthesis. And obviously, it is semi-polarizing topic, because when we talk about education and students, pupils using AI for everything, is like, okay, are you still thinking, or are you just like copy pasting into those chatbots? In the research world, the journals that I read mostly basically require you to disclose that you use this AI tool, what you used it for, what, like at which stage of publication you used it for. And there's a learning curve. I was a reviewer of a publication that where the authors were assisted by AI, and it did sound like AI, but because publishing is a peer-reviewed process, they got feedback from the reviewers, me included, that, hey, the content is good, but like work on how you deliver this content. It cannot sound like a cheap version of ChatGPT. Let's make it sound like you, or like an expensive version. Anyway, so you have these tools for researching your literature, for outlining content, brainstorming. Like the thing that is super powerful for me is you can now gather unstructured ideas in a meeting, in a brainstorming session from people. You have a transcript of this, and you don't have to manually go through it to structure it. You can have AI structure it, and then you go already through the structured version, and you can give it to your collaborators for another round of comments and another round of comments until we decide we don't take any more comments. But in any publication, it's a lot of rounds of these things. So I'm excited about this. And actually, a fellow veterinary pathologist, and Dr. Candice Chu, she perfected flow for this. And when you Google her, she has a cool framework how she writes publications with AI assistance to be a lot more prolific. So that's super cool. And obviously, this discussion wouldn't be complete without mentioning of regulatory consideration. But we're very lucky, because in this series, in the publication number, let me check, 5, we have regulatory aspects of AI and machine learning in medicine. And if you are thinking about the regulatory considerations, frameworks, guidelines, you must go to number 5, because when I was reviewing this, and whoever was here on the live stream, I had no idea how many guidelines already out there. Like, you don't have to reinvent the wheel. Go to Livestream/publication number 5, regulatory aspects, and you will know what to take into consideration, which frameworks you have to be aware of, what are your guidelines wherever you live, wherever you work. But before we go, let's look at another image. So this is virtual education in pathology. Super cool. I love the images. Virtual reality. So learner is completely immersed in self-contained digital environment. So, it's digital, but the skills are real. So this is super cool, because the material you are using is virtual. It's magic. I don't know. I'm just super excited about it. But the skills are real. So if you then get real material, you have the skills. This is so cool for me. So you have these goggles that they have, and you have remote controls usually needed to control virtual hands due to total enclosure in this environment. And there are 2 approaches. There is this virtual reality and augmented reality. For example, virtual would be Meta Oculus Quest. Valve Index, HTC Vive, and Augmented is Apple Vision Pro, Microsoft HoloLens, X-Real Air 2. I think I used Apple Vision Pro once, and I don't know if anything else. But you can do virtual reality cadaveric dissection, virtual reality histology learning. This is super cool. And then in augmented reality, you can also have both, but then it's like a combination of your real world and the digital. So augmented reality, the learner interacts with holograms, whereas in virtual reality, you become like an avatar and you enter that enclosed world. So they are superimposed. The holograms in augmented reality are superimposed into the real environment. And yeah, you have different goggles, and you can have the possibility to use one hand as controls. And these were the Apple Vision Pros. I checked them at a conference at the booth of a company called, I'd like to investigate if they have histology learning in virtual reality. So yeah, this concludes our 7-part series, and it's not actually my series. My series is just the Livestream series, but it's Modern Pathology, written by a team from Pittsburgh that have an center of excellence for AI and digital pathology. If, as some of you are here for the first time, then maybe you want to learn more about digital pathology. So I would recommend you download my book, Digital Pathology 101. The Digital Pathology 101 book I also have in a normal version. Let me just sharing this. In a paper version, you can buy this on Amazon or just take the free PDF. It has an AI chapter. And what I'm going to be doing, and if you already have this book, keep it, because you're going to get an updated version. Everybody who has the book, I have a list of everyone who's there, will get the updated version where the AI chapter, let me see what chapter that is going to be updated with, chapter 3 specifically, and the whole book, because I published it in 2023. So, hey, digital pathology time flies faster. I'm going to be updating it. And if you have the old version, so if you now download it, it's going to be the old version. Doesn't matter, because everybody who has the old version is going to get the new version once it's out. So thank you so much for joining me. Thank you so much for staying till the end. It means you are a true digital pathology trailblazer. And I talk to you in the next episode.